Welcome everyone to our webinar today. Thank you for your time for being here. Today we will talk about Conquering Mars. This is part 1, and it's about the unbeatable duo Discovery plus OptiSLang. My name is Jose Mendez, and for today we have an agenda that goes like this. We have first a presentation, then we talk about a new approach to landing on Mars. Then we can see how valuable is low fidelity data. Then we will see what Discovery is and why we should use it. Then we also go to OptiSLang, why customers are using it. Then we will take a look at our problem today. Then we will see the project outcome, and then we will have a wrap-up session at the end where we can read the questions and go through comments. In this presentation today, we want to answer your questions. You can do that by filling in the fields on the panel, the questions side in the panel, and we will read them at the end of the presentation. So who are we, these crazy guys trying to talk about this idea about conquering Mars? Well, I work for EDRMedeso. We're a company and we're about people enabling innovation. We are operating since 1986. We have around 50 million euros in turnover and around 160 employees. And our customer base is consisting of more than 1,000 customers. We work in mainly in 5 countries, the Nordics and England. We have different offices, and I particularly sit in Gothenburg. So west coast of Sweden. My name again is Jose Mendez. My education is in mechanical engineering. I've been working with digital simulation for around 10 years, and I have around 7 years of experience with Ansys. If you want to connect on LinkedIn, you can do it. Please feel free to do that. Then let's go more into the story about a new approach to landing on Mars. And for that, first we have to introduce our 3 vehicles for this story. So first we have Olympus, that is the ascent-descent vehicle. Then we have the Legacy, that is the launch vehicle. And then we have Echelon, that is an interplanetary transfer stage. I have to say that this story is by Eric Koo, who is an aerospace engineering student at the University of California in the town of Davis. You can find more about it on the internet. It is from the year 2022. Now, I'll try to put this story in the task to see exactly what it is. It is still a science fiction story. It has still a lot of fantasy, and some parts of it are becoming more and more a reality, okay? So first, take off with Legacy and Olympus. Then we land Legacy like Falcon 9 SpaceX example, if you've seen it. Then Echelon is built in space. Then rendezvous Olympus with Echelon. And then transit to Mars. land Olympus and use it as an operation base, ascend back to orbit and dock with Echelon, and then transit back to Earth, Starship style landing with Olympus, and then the last step is refuel and resupply Echelon for future missions. So let's go into our next topic, that is how valuable is low fidelity data. So if we take a trip on the time, we know that long ago before, we were working with concepts, ideas, trying to create new products or services to be delivered to the market. And then at some point, digital simulations were introduced with the rise of computing, when computing power was increasing and when it became easier for people to use this technology, more affordable and so on. But we see that the amount of time in this transition dedicated to digital simulations was short. And then people back then use heavily or rely heavily on physical prototypes. And of course, we always want to find new ways and to reduce waste, to make things more affordable and easier to be done. So there was a question about how to reduce this time, and the cost associated with physical prototypes. Then after these physical prototypes, we have, of course, the ideal is to have better products, and then they will be released to the market. Now, I think that today we use simulation as a tool for reducing test costs and for gaining insights from our designs. And we have compressed the physical prototypes expenses and time dedicated to it before we release the product to the market. Now the question is how to reduce simulation run time, how to tackle the riddle of a faster time to market. And then what about a future where we can deliver products to the market faster and further through low fidelity data and using artificial intelligence? I believe that we could obtain feedback for designers and system engineers and architects, pointing challenges out early in the design, production, and validation stage. So we rely a lot today on high fidelity data, namely traditional simulation tools or analytical models. Usually the challenges that customers are facing today is that the complexity of the problems are increasing, and for example, introducing factors such as multiphysics and more larger problems, trying to represent more complex cases. Before we can, we want to go through different stages such as validation, and companies want to make sure that the quality of their products are according to their requirements, according to what the market expects. And for that, we rely little today on the use of low fidelity data. So we could say that we use it still in a low scale. Now, I think that low fidelity data will replace high fidelity data in the near future. And there is also a concept named synthetic data, which is entering the engineering arena today. And I believe that low fidelity data is useful for optimization tasks. Then we go now into the first tool that was used in this project, and that is discovery. And perhaps the best way for doing that is to show it in a video, okay? And this video will see why Liebherr, a German-Swiss multinational equipment manufacturer based in Bühle, is intensively using discovery in their engineering core processes. So I just ask you for 4 minutes of your time to watch this video, and then we continue with the webinar. So we come back again to the presentation. And regarding discovery, I want to say that if you are here in this webinar because you are more interested on it, we have currently in our training portal a training on discovery for next year. And you can find more details at our webpage, EDRMedeso.com. And it's about a hybrid training, okay, online and on-site. And on-site it will be in Gothenburg. So now we move into OptiSLang. And why OptiSLang? Simply to reduce time to market, to deliver better products and with a good quality, and to finally save time. Then what is OptiSLang then? Well, I think that OptiSLang is a general purpose optimizer of parameterized models. And typically, the way how it works is that first, the foundation is a parametric model. And then we have on top of it, we have 2 stages that are understanding and optimizing. And in understanding, there are many things that are ongoing in there. And one is a dedicated data set that is created for your unique problem. It could be a simulation or an analytical problem. And then we have the optimize, and that is upon either your real problem or a model that is a simplification of yours that is done through machine learning training on the data set that was created before. Then the next step could be to automate workflows, depending on your case, and even to introduce robustness analysis. And we have others add-ons, such as creating web apps, or where you take your trained models into a server, and everyone could access these models and run them into a well-defined condition sets. And we can usually or actually use more advanced machine learning algorithms if you have a large data set. It could be data that you have from engineering, from test, etc. Then the final goal again is to, the mission is to achieve a digital thread in your organization, meaning that you can automate things and share information and improve the communication and the collaboration in your teams with the goal of reducing time to market. Now let's go a bit into our problem. Well, and now I have to introduce a bit of the framework that we are taking a look at. So what we see here is a Hermes spacecraft. I don't know if you have seen the film The Martian, and it is based on a book with the same name. And they have a Hermes spacecraft that and is the crew transport spacecraft of the Ares program, and it's built to transport astronauts from Earth to Mars orbit and back. Hermes was constructed in low Earth orbit using the SpaceX space station as a building platform, with individual parts transported to stations piece by piece, and the process was tedious, but its results established a new era of space travel. Then, if we take a look at the engine of this spacecraft, it is the name is NERVA, and it is a nuclear rocket engine, and the name comes from the nuclear engine for rocket vehicle application, and it was a nuclear thermal rocket engine development program that ran for roughly 2 decades. We have different parts in this engine. We have turbo pumps, we have external disc shields for the radiation, internal shields, we have the reflectors, we have the reactor core in here, and we have the nozzle. And then we have this nozzle skirt extension. That is the part that we are interested on. Now, as I said, this is an old program from the 1670s. And now today, post-NERVA era, there is still post-NERVA research. In January 2023, NASA and the Defense Advanced Research Projects Agency announced that they would collaborate on the development of a nuclear thermal rocket engine that would be tested in space to develop nuclear propulsion capability for use in crewed NASA missions to Mars. Now, going into our design more in detail, we see the whole sort of engine here that is attached to the Hermes spacecraft, and we are interested on the nozzle skirt extension in this area in here. Here I could draw the geometry for easier understanding, and this is how we have tackled the model, and we have taken into OptiSLang. And particularly the problem, we have the skirt extension, then we have a load that is acting, connecting to this edge, and then we have a moment that is attached to the pin between the nozzle base and this column. And this is how the deflection for this column should be. So it is a mechanical problem application, and what we are trying to model here is a condition that exists during high accelerations for this spacecraft, particularly at the beginning when we move this mass in space. The way how it behaves in this particular mode is depicted here in this animation. We have two input variables or parameters, and those are the radius of this column and the length of it. And the responses that we are interested in are the mass variable of the column and the maximum displacement of it. And our objective in this project is to optimize two responses, namely the mass and the maximum displacement at the same time. Now I will go more deep into the details on the discovery side. And for that, I'm going to go through this video, trying to show how the tool looks like. So here on this panel, we can choose, for example, to visualize the components that we want to. We can change the color of them. We can then visualize them with different colors. We see here the full engine with all the different details and the colors. Then at the top, we have different tabs where we can repair the geometry, we can remove areas of low quality, and then we have this simulation tab on top, and we have different options in there, and we have the possibility to move this project into a traditional tool like Mechanical or Fluent or Workbench. And here we see the materials. This material set is coming from Granta. We have around more than 4,000 different materials, and we are on the model mode. We can go into the explore mode, and then we can run the results. We see in the panel the different boundary conditions for this mechanical problem. We see gravity, for instance. We see the supports, the kinematic boundary conditions, dynamic boundary conditions, the loads. And we can define all these inside this tool. Then we have here at the top the fidelity area, and that is an important one, right? It's about the accuracy of the model. We can set up the fidelity approach. We change here the mesh size for this tool, and then we can decide how accurate we want it to be. This is a tool that is using your GPU to solve it and to give results really fast. I here click to solve this model, and then it's already giving you some results. Okay, it's doing some iterations, and meanwhile you can come and you can select which part you want to see. You also select which part or components you want to include into the simulation. Different options in there, visualization stages. I can pause the simulation, and we can also monitor different variables or results or plots and different types of results. We see how these result variables are converging to the final value with different iterations. We pause again the simulation, and then we can see here a parameter manager, and here we can see what the values are for those parameters. And this is an important part because, as I showed before, this is the stepping stone of our next tool, that is OptiSLang. We need a parameterized model. Then at the end, we can even move to the refine mode, where we can click again to run the simulation, and it's actually going to use the traditional solver. So in this case, it is going to run a mechanical simulation. It will create the same mesh as it would do on mechanical, and you will be able then to get that result without moving to that high fidelity tool. So if we go next to our next tool, that is Discovery. Well, first we use Discovery because we can achieve results very quick, still on a low fidelity mode. And what we are going to do here is to connect that tool into OptiSLang. So I open the project, I can drag a wizard into it. Here I can drag that discovery model to make the connection. We see here the parameters that we saw inside Discovery. We select the responses that we want to use, also the input variables, and we can define here the range that we want to use for them. We can save those parameters also in a file, and we can reload them. I can save this template for later on. And here, what I have created is the connection, right? I'm doing a check that everything is well connected. And after that connection is done, I create a so-called sensitivity system, dragging that into our model. And here I can copy paste the same parameter set. Here, this step, what I have done is to, if I let it be a little bit forward, I have selected the constraints before and the conditions, the responses in here. Then we continue. We have here different algorithms for the sampling set, different steps. And then here, pay attention to this part. If you have a large amount of data, you can come to this window and this tab, and you can select to use a deep forward network algorithm that is integrated into this tool, again, when you have a large amount of data. So we continue here after this setup, and I give some naming to it, and then when I click play, we'll see that the OptiSLang is just taking automatically and running all those parameters and doing all those iterations, and with many different variations that are done automatically, that you don't have to decide which points you have to select. And this is the part that takes most of the time for the very localized small pool of a data set that is going to use to represent your particular problem. And we can monitor the progress as it runs, what's happening with each design. I go back a bit faster, and we see the progress, how it is going on, okay? It is running, we go back, we monitor, and then we get some results. For this particular case, we run around 100 design points in about 30 minutes. This tool, after that, it has a post-processing module, and we see here the response. We see all the data that was generated in the space that we have selected for the ranges that we have chosen that we want to explore. And we see the response surface that is coming from that model that is based on the training for this data. And we can visualize which parameter is more important than which. For instance, in this is the radius, and we see interaction effects between them. We can use different tools for post-processing this data. For example, I have used, in this case, a cluster analysis to find trends through colors. And we see that those colors for the cluster analysis are transferred to all the windows that I have in this post-processing tool. And then coming back to the model, then we go into the second sector that is optimizing the sensitivity on top of the sensitivity analysis. We do that through the wizard. So we see that all these workflows that we are creating in here are done automatically by OptiSLang. So we can say that this is a low code, or in this case, no code machine learning tool. We copy paste the same parameters from before, we keep the same responses. And I want to go back a bit. This part is important because again, the responses, and then the next window. Here we decide which model we want to use. If we want to use our real project, or if we want to use the MOP model, that is to say the trained model that is done based on the data sets that we have used for training. And the software will We have different options, and it will recommend to us the algorithm that is better suited for this purpose, for optimization again. So we can define with how many designs we want to validate, since we're using the train model. The workflow is, again, automatically created by OptiSLang. This tool offers a lot of flexibility, meaning that you can tweak these workflows and if needed, if you want to add extra steps, if you want to connect different tools, for instance, Excel or MATLAB. We continue forward. And after the naming, I can start the optimization journey. Now you see in real time how fast it is when we select the MOP as the base for the optimization task. So it has run already 10,000 points on the optimization part using the train data or using the model that has been trained through the data set that we have created before. Again, we can see the progress for all the systems inside the scenery. And I go a bit behind. Then it goes into the next stage in this workflow, that is the validation of those designs. And for that, it is basically taking the same discovery model that we have created from before and done the validation stage. So we see that it is amazing fast. So then it gives us this in this post-processing window for optimization, the so-called Pareto plot. So we have the two variables or functions that we want to optimize: the mass of the column and the displacement, maximum displacement. So we don't actually get one single point, but we get in reality a front with different options. And the reason is that these two functions are in conflict with each other, meaning that minimizing one will maximize the other one. So we need to find a trade-off. Again, more into the post-processing, we have different options to visualize what the values are for the different parameters and responses. And if we have constraints, we will see them here. I select different points and I can play a bit with the optimization. So that is about OptiSLang, okay? Now, let's go to the project outcome. And for that, again, we show here the Pareto plot or Pareto front, and we have the displacement as an object on this axis, and we have the mass on this axis. Then we see two curves. So the dark curve corresponds to the discovery model, and the light blue one corresponds to a high fidelity tool results, and in this case it is exactly the same model inside Workbench. And if I go further, we could draw a rectangle trying to cover the common areas on both axes. And then if we take the optimum that we obtain through the low fidelity tool, in this case discovery, and then with the same input parameters, we read the value for the high fidelity tool, we get this point in this curve. Now, if I go back and show again the rectangle, we see that those 2 points are inside the same area. And at least for this case, we can say that if you don't use your high fidelity tool, you can, in a scientifically and documented way, say that you have optimized your model. Now, going to more into comparisons. So the best design from discovery is for is the combination of these two input parameters. And by the way, the moment that was applied to the column, it doesn't influence the results significantly, and OptiSLang has taken it away. So again, going to the discovery results, we get this mass and we get this max displacement. So 41 kilograms, and then reading exactly the same results from the high fidelity tool workbench, we get 44 kilograms in mass, and it is around a 7% indifference. And if we compare then the displacement, we have a 13% indifference. So yes, there is still a difference on the values themselves, and that's still the state of the art for our so-called low fidelity tool. Now, the trend that we see in the market, and the vision that Ansys has, is that this gap is closing as time passes by. I'm not an expert on the fluent side, but what I know is that on the fluid side, the difference is getting even shorter than this. So now let's go into a wrap up for this session. So we propose a new process with the whole idea, and because we want to reduce time to market to deliver products faster and further. So we first use the discovery software to parameterize our model. Then we parameterize that model. Then we move that model into the OptiSLang platform. Then we create the data. Then we apply machine learning model for training that data. And then we optimize on top of the trained models. And then finally, and pay attention to this part, we can use the high fidelity tool as an appraisal control. So we do a high fidelity switch just as an appraisal control at the end of this workflow. Now, what is the main reflection then about this project? Well, ta-ta! It is possible to find an optimum with low fidelity data. And here my email for comments, or if you have a project that you believe could be a good candidate for something like what we have done, namely if you are spending a lot of time on models with a large simulation run time, or if you want to take a discussion on the morality of this low fidelity versus high fidelity, if you want to take a look at the results in detail and all the files, we can run an audit on it also, if you would like to check the how we have done it. So feel free to contact me on this email. And so having said that, now I want to thank you for your time. So, and this is the moment. If you got any question, feel free to drop it on the chat or on the questions panel here on GoToWebinars. So let's give it some minutes to see if someone. So if there are no questions, you can, of course, feel free again to send them to me through using my email address. And again, I want to thank you all for your time. I appreciate it a lot. And have a great day. And I hope that you success with your projects and your endeavors. Bye-bye.